How do rovers drive on planets without direct teleoperational control? This is Mars rover Perseverance on its 3-mile journey to the Jasvia River Delta. We need to cover this distance as fast as possible to give scientists as much time as possible to explore the delta. In order to do that, NASA cannot manually drive the rover, which means autonomy will be required. This video will cover a small part of the autonomous driving process by looking deeper into path planning, a small but very important step in this process. So in easy words, how and on which path do we get from point A to point B? And is this even a good path? But first things first, let's look at the problem from a little broader scale. This is a brief schematic representation of the basic steps a rover needs to cover in order to drive autonomously. The most common algorithm used for this is SLAM, which stands for Simultaneous Localization and Mapping. In order to localize the rover and create a map, SLAM needs two types of input data. First of all, it collects sensor data. These can consist of odometry data, like wheel encoders, information about rotation and other inertial forces detected by an IMU, or velocimeters for speed. Besides that, there are many other ways of gathering sensor data. We need a second set of data collected by stereo cameras or laser scanners in order to improve our sensor data. This is usually done by some sort of bias filter in the SLAM algorithm. Additional to that, cameras and laser scanners are crucial for the detection of obstacles and boundaries. With both that information, SLAM, by a bit of driving around, can now obtain a detailed map of the before unknown environment. We can see here that the prediction gets better each time the robot crosses a point where he has been before. This process is called loop closing. The map and position of the robot is now given to the path planning algorithm. A good path planner should return optimally the shortest path as a list of waypoints which the rover can travel to, step by step, without hitting an obstacle or getting stuck. But what if we do not have all the necessary tools to implement a good SLAM algorithm? So what if we cannot obtain the necessary map and rover pose for a pathfinding algorithm? Well, there are ways to navigate through terrain without knowing anything but the goal where we want to be at the end. The answer are bug algorithms. There are three basic ones of them. Let's start with bug 0. The algorithm is as following. We first start at our start point and we head towards our goal until we hit an obstacle. If we hit an obstacle, we turn left in this case. There are also right-turning bug algorithms. We follow the obstacle until we can head directly towards the goal again. This process is repeated over and over again until we hit our finish line. But be careful, bug 0 is not guaranteed to work. If we have an obstacle like this, our path would look like this. We would head directly towards the goal, then we would turn left, and then we would follow the obstacle until we can head towards the goal again. We would be stuck in this circle forever. This is the Polyrobot app developed by the University of Bonn. I will show you in this app some examples for the previously described bug algorithm. We start up by drawing the environment with obstacles. We go to the Explorer and see that we got our starting point. We can now, over the option Move to Point, add a point, which is our goal. We can now select our strategy, which is first of all bug 0 in this applet named bug 3. We also choose a right-handed bug, which means he will take left turns. We can now run the whole process through. After restarting, we can also run separate steps and watch each step. He first turns left when hitting the obstacle, Then he follows the obstacle until he can hit towards the target again. Then he follows towards the target and repeats the thing once he hits the obstacle again. If we want a bug algorithm that reaches the goal with a higher percentage and in more complicated areas, we need bug 1. Bug 1 takes quite long paths. He starts also by hitting directly towards the goal, but once hitting obstacle, he completely circulates it, and once he circulated it, he detects, while the circulation, the shortest path or the shortest point in direction to the finish. He then moves back to this point and then moves in direction to the finish point. Once again here, he hits an obstacle. He moves completely around the obstacle until, and during this circulation phase, he detects once again the closest point to the finish. Then he moves back to this point, and from there he moves to the finish. Once again, a little demo in the polyrobot applet. First of all, we let run it through. So first of all, we gotta go left because we hit an obstacle. We follow the obstacle until we completely surrounded it, detecting the shortest path, the shortest point to our goal. After surrounding the obstacle, we choose the shortest path to our detected point. From there, we head on to our goal. The third and last simple bug algorithm is the bug 2 algorithm. Here we have a line given from start to finish. We follow that line until we hit an obstacle. We left-handedly circumvent the obstacle, but we don't head towards the finish again as soon as possible, but we wait until we hit the line again. And if we hit the line, or when we hit the line, we head towards the finish. Also here, the little explanation in the polyrobot applet. We first of all run it through, and we can see that it's quite similar to bug 0, but with the line. If we run step by step, we can see the differences. We head towards the line, and then until when we hit the line, we head towards the goal along the line again. We repeat the process, but we follow the obstacle until we hit the line and then head towards the goal. There are more advanced bug algorithms like the here shown tangent bug. It works with a sensing area. Once an obstacle is detected, we can take evasive actions. This improves our generated path by a lot. Well, okay, we now know how bug algorithms work and how we can navigate through a terrain without knowing too much about the map. But what if we have a maze in front of us? Or even more realistic, a complicated Mars surface, like shown here. We cannot just wander around and hope that somewhere, somehow, we can find a valid path to our destination. We need proper path planning. To find a valid path in a topological map, there are basically three methods: breadth first search, depth first search, and best first search. Breadth first search starts at the tree rod and explores all nodes at the present depth prior to moving on to the nodes on the next depth level. It terminates once a valid path is found. This must not be the best path, just a valid one. Depth first search explores the path as far as possible along each branch before backtracking. Extra memory is needed to keep track of the nodes discovered so far along a specific branch, which helps in backtracking of the graph. Like breadth first search, it terminates once a valid path is found. This must not be the best one. It is likely that depth first search finds the path faster than breadth first search because it searches more aggressively towards the goal. But it is important to note that depth first search may not terminate in some cases. For example, if there is a path quite long and the heap or stack runs full, it will not terminate because it cannot save all the paths above. For infinite paths, this is the same problem. best first search algorithms actually search for the shortest path. It uses the distance between the starting node and the goal node as heuristics. Most of the robot path planning algorithms are actually best first search algorithms, so we're gonna have a look into them a little bit deeper. Well, before we look at the path planning algorithms in specific, we need to look at our obstacles again. Because for each obstacle, we need to include a space around it, called the C-space. That's a space where the robot actually can't go from its middle position because of the dimensions of the robot. So in this specific example, we can't fit with our circular robot through these two obstacles because the C spaces are overlapping, so we need to find a different path. For three-dimensional objects, we do some kind of a cylinder approach, where we just wrap a cylinder around our obstacle, and then we can increase the size of the obstacle by the given shapes of the robot. So now that we know the real spaces obtained by the obstacles, we can calculate a path. But for calculating a path, we need to first of all create a grid in our map. So we can go from node to node because path planning algorithms always work with nodes. Well, first of all, to create a grid, there are two different approaches. The first one is the standard one. We just divide our C space, this with the obstacles is the C space, into a grid within a specific size. That's quite fast done, and we can do it very reliably. The second approach would be the approximate cell decomposition. Here we divide our whole map into not equally sized grid cells. We just do as many as we need. So for instance here we have a quite large white space, so we can do a large cell. In proximity to our obstacles, we need to do smaller cells because large cells wouldn't fit here. This is way sophisticated because we don't have that many nodes to search for, which makes our pathfinding algorithm way faster. But we as well do not lose the required fineness in proximity to our obstacles, which we require to navigate around them. The approximate cell decomposition works with the principle of a quadtree. Starting with our working area omega, we divide it into 4 cells. We name them clockwise and add them to our quadtree, here marked in red. We then repeat that process for all the cells that contain parts of an obstacle in them. So part 1, 2, 3, and 4 all contain some snips of an obstacle. So we just divide them again. Our quadtree gets extended by the 16 newly generated cells. I named 1.1, 1.2, 1.3, and 1.4. Of course, for all the other cells, they will be named and put to the quadtree as well. Now we can see something different. Cell 1.1 and 1.4 do not contain any parts of an obstacle anymore, so we do not have to divide them any further. Shown here in yellow, we divide the mixed cells. This cell composition has to be repeated over and over again until we reach our designated resolution. At the end of the process, every grid cell that has no longer any obstacles in it is called an empty cell. These empty cells can be visited by our robot and can be added to a list for a pathfinding algorithm. Now that we got all preparations done, we can finally look at our algorithms. We want to look at Dijkstra's algorithm, the A-star algorithm, and the sophisticated A-star algorithm, D-star. Let's start with Dijkstra's algorithm. I want to show it to you by a quick example. We start Dijkstra's algorithm off by initialization. We set every value to infinity but a. A is of course not infinity, a is 0 because we are starting at node a. So in our first iteration, which we will be in the same column right now, we go to the letter B and C, which is from A, of course, 4 and 7, and with the previous letter A. We now looked at every node, which is reaching from A, so we finished A. In our second step, we look at the cheapest. The cheapest is B, because A is ready, we don't count A, so we continue with B. From B we can reach to C, D, and E. A does not count because it's already finished. From B to C is 4 plus 1, which is 5. From B to D is 4 plus 3, which is 7. From B to E is 4 plus 10, which is 14. We reach them from B. And we take down the 4 and A from previously, and they we cannot reach yet. B is now done as well. The next cheapest letter is letter C with the value of 5. From C we can reach D and F. D would be 7 plus 8, which is 13, which is way more expensive than the 7 we got above, so we just take the 7. F from C is new, it's definitely lower than infinity, so we take 7 plus 5, we take 5 plus 5 because we always take the cheapest route. 5 plus 5, which is 10. We copy down all the other ones we can't reach from C. We calculated previously. And C is now done as well. The next cheapest letter would be D with 7. We move from D to E and F. E with a cost of 4 plus 3 plus 5 is like 7 plus 5 is 12, sorry. And to letter F, which is 8. They are all both improvements from before, so we take the new route. Like beforehand, we copy down all the ones we don't reach from this specific knot. Still can't reach G, and letter D is now finished as well. The next cheapest letter, or knot, would be knot F, reachable in 8. So from F we can reach E, and we can finally reach G. So 8 plus 3 to E makes us a value of 11, which is cheaper than beforehand. And to reach G, we can now make 8 plus 9, which is 17, to reach G. We copy down all the remainings from above. And letter F is now done as well. So now we got ourselves the last step. We check for letter E. Letter E is our next cheapest. So we go ahead. From letter E we can go to only to letter D because he's the last standing letter, which would be in 11 plus 4, which is 15. And we copy down all the values from above. And now letter E is finished as well. So now we got ourselves a nice little table with all the values and all the costs and all the previous letters. But what are we gonna do with them now? Well, how do we get the root? It's quite simple. The lower part gives us always the next letter we want to go to. So from G, we're going to E. Then we go from E to F, from F to C, from C to B, from B to A, and then we're done. We now know that knot G is reachable with a cost of 15 over this given path, which is also always the cheapest path we find with this algorithm. Alright, so we went into a detailed example about Dijkstra's algorithm. Let's head over the A-star algorithm a little bit faster because it's essentially an extension of Dijkstra's algorithm. We take into account heuristics as well. So we got the old paths like 4 and 1 and 7 or like that. But now we know actually how long we take to go there by measurements. Like the path is 4 kilometers long, but we know that we need to walk 6 kilometers to be there because maybe it's not round or maybe not the straight way, or maybe it's like some bushy terrain or something like that. Yeah. So now we add up the heuristics with the known path length or with the given path length, and this is our new path length. And so from A to B is 10, from A to C would be 9 then. Like in Dijkstra's algorithm, we now look at the cheapest node, which is node C. Node C can expand to D, F, and B. Node B is more expensive here, and it's doubled, so we don't take into account node B because it's cheaper in another way. All right. So now, what's the cheapest letter? The cheapest path. The cheapest path is B with 4 plus 6, which is 10. So we continue with expanding B. From B we can reach E, D, and C. C we don't count because C we already visited. So we cross it out. Now we expand once again the cheapest path, which would be then D. And by expanding and expanding even further and further, we reach the whole pathway. And A star does terminate if the G is the cheapest path, because it is possible that we reach G beforehand, but G is then not the cheapest path, so we expand other nodes beforehand, and it terminates once G is the cheapest path. A star is very potent in average case situations, but not that good in worst case scenarios, because a replanning of the map is often necessary if we hit dead ends or something like that. In order to circumvent such problems, D-star or D-star Lib was developed. Shown here is a map with closed doors, but the algorithm assumes they are open. Once coming there, normally a complete recalculation would be necessary. D-star does not have to do this because it uses back pointers to previous positions, so a complete recalculation is not necessary. With all these new algorithms and sensors Perseverance got, he broke already every driving record on Mars. Technology is evolving, and I'm curious what future is providing us.